Hello and welcome back to LFI Debates. Let's discuss about refracting telescopes. Telescopes are those optical instruments which are used to view heavenly bodies like moon, star, planets. We use these refracting telescopes. Telescope, how it works, it will come in two cases. Case 1, when the image is formed at infinity. Generally, when we use telescope, we get the image at infinity. Here also we use two biconvex lenses of different aperture and different radius of curvature or different focal length, we can say. The objective lens that faces towards the object and the eyepiece lens that faces towards the eye. In this case, unlike microscope, objective lens was of shorter focal length, but in telescope, the objective lens is of larger focal length. This is your objective lens. You will draw the lens one at a time. Just keep in mind that the eye lens must be smaller. This is the optical center, suppose, for the objective lens. You have to take the rays that comes from the distant object parallel to each other. This way you will take it. They are coming parallel to each other. Keep in mind that this angle you have to take it small and see that these two are parallel to the principal axis. The ray which passes to the optical center, as you know, it just passes straight. This ray will converge slightly because this is a convex lens. It will converge like this and will form one image here. Let me mark this image as AB this time. The object, we can't see it, is very far, so we'll start with AB. Let the size of the object be, image be I. This is your image produced by the objective lens. Now, the image which is produced by the objective lens, there you will get the principal focus of the objective lens as well as the principal focus of the eyepiece lens is coinciding at this point. Now, if you take a small eyepiece lens, the focal length of the eyepiece lens you can see from O to FE. This is your eyepiece. This lens is your eyepiece lens. The ray that will come parallel to the principal axis must pass through the principal focus. This distance, mind it, exactly you try to take here, FE. It will go, if it comes parallel to the principal axis, then it will pass through the principal focus of the eyepiece lens. Like this it will go, or it will pass. Then the second ray, you'll have to use your scale. It must be straight. It will go like this. Then the second ray, if you allow it to pass to the optical center, then it will just pass straight. These two rays you can see very clearly that they will be parallel to each other. But if these distances are not equal, then it will never be parallel. So you need to be very careful. Here you take 3 cm or 2 cm. Here also take 2 cm. Or 1.5 centimeter, 1.5 centimeter, then it will come by itself automatically. This way it will pass. You are observing from here. The rays are entering your eye, and then you will see the image at infinity. You will see the image at infinity. So this is how it works. Object coming from the object was placed at infinity. Image also will produce at infinity. observing the moon from Earth, if it appears like a football without telescope, if you use a telescope, it will look much larger than the football, 100 times bigger than the football, depending upon the focal length of the lens that you are using. So in this case also, magnification you define like this. While looking the final image, the ratio between this angle beta, and this is the angle subtended by our eye at the final image while viewing the final image, divided by the angle subtended by our eye while observing the object. But when you consider the distance of the object from us means we are here, this distance is negligible. So we neglect this distance and we take this lens and here take this angle alpha. So our magnification M, or magnifying power, of a telescope M, we take it as beta by alpha. But as we know, if this angle is alpha, they are vertically opposite angles. So here we can take this alpha. And if you take this as alpha, then you can find the ratio between tan beta and tan alpha. Your triangles will be A, B, let it be O dash. In triangle A, B, O dash. In right triangle A, B, O dash. Tan beta, it will be defined as perpendicular. I took the size of the image as capital letter I divided by this distance A O dash, and A O dash is what you can understand. This is the focal length of the eyepiece lens. Fe is present here. Focal length of the eyepiece lens. And generally we don't take this first focus when you discuss about lens. We take the second focus. But as it is towards our left, we'll take it as minus Fe. We'll take this as minus Fe. So from here we can get beta I by minus Fe. When angles are very small, then beta we take it as beta. Likewise, in right triangle ABO, this one ABO, we can find tan alpha, and tan alpha will give us alpha. Tan alpha will be perpendicular, that is AB, divided by base, that is OA. Now AB we are taking it as I, the size of the image or height of the image. OA is what? If you look carefully, here itself FO also coincides. This is the principal focus of the objective lens, and this distance is called the focal length of the objective lens. We write it as small FO. But this time for objective lens, the focal length is on the right hand side. We use this focus right hand side, so right hand side we take it as positive. FO will take. By putting these values, this will change to alpha. By putting these values of beta and alpha, you can find out the magnifying power. So magnifying power M is equal to beta by alpha will give us, beta is minus 1 by Fe, or not 1, it is I by Fe, and here you have I by FO, this is the value of alpha. So ultimately magnification M is equal to minus I by Fe into FO by I. This I you can cancel it out, and you can get the ultimate expression. Magnification is equal to minus FO by Fe when the image is formed at infinity. Now let us see the second case, case 2. That will be under normal adjustment, how to get the image at a least distance of distinct vision. If you think you'll get it, how to get this eyepiece we can adjust, we can bring a little bit nearer so that the focal length will go this side. And if the image formed by the objective lens is between the principal focus and the lens, then the image will be formed at near point, that is at the least distance of distinct vision. Let us take the second case, case 2, when the image is formed at the least distance of distinct vision, that is near point. Distinct vision. That will be under normal adjustment in your telescope. This is under normal adjustment. Under normal adjustment, as I said before, here also the rays that will take from infinity will come parallel at a smaller angle here. This angle should be very, very small. And then the first ray will be formed at the principal focus of the objective lens. That is AB is written there. Now, when you take the eyepiece lens, you adjust the eyepiece lens in such a way that it will come somewhat nearer to the image. You can adjust it in a telescope. The eyepiece lens is adjustable. When you bring the lens nearer to the image that is formed by the objective lens, then its principal focus, let it be O dash like before. Let it be O dash. Its principal focus will move somewhat like this, FE. That's you are bringing the lens nearer to the image from the objective lens. Then you can start drawing the rays. A ray that goes parallel to principal axis must pass to the focus. Mind this focal length. We'll take it almost at the same distance. I'm taking it here FE. Then the ray which will go parallel to principal axis must pass to the principal focus. And the second ray, if it passes to the optical center, then it just passes straight to the deviation. These two rays, they are diverging, they will never meet each other. So you need to produce the line, both the lines will produce it, and then they will come and meet at a point. There the image will be formed, the final image will be formed. So this is your final image as B dash. And this will be formed at this distance of distinct vision D. Now, how it works, then you should be able to say very clearly that when an object is placed at infinity, the first image that is formed by the objective lens is produced at the principal focus of the objective lens, that is AB. This image of the objective lens acts like an object for the eyepiece lens. And then this lens magnifies the image and makes it larger, and the final image is formed at as B dash. So this is the working principle of refracting telescope under normal adjustment. Now to find out its magnifying power, as you know, M is equal to the angle subtended by the eye or at the eye while viewing the final image, that is beta. This is the angle subtended by the eye while viewing the final image, and then divided by the angle subtended by the eye while viewing the object when placed at a least distance of distinct vision. But in this case, as I said already, telescope, this distance is negligible compared to the distance of the real object from the telescope. This length is very less, and this side the length from the telescope to the object is very, very large. So this part we fully neglect it and take care of this alpha divided by alpha. And like before, you can find out tan beta and tan alpha. From there you get beta and alpha, and after that we put the value here. So M we can write it as beta, I can write it as tan beta, divided by alpha, you can write it as tan alpha for small angles. Now beta, when you say tan beta, it is AB divided by AO. It is AB divided by AO. And tan alpha, when I say, it is AB divided by AO. Sorry, this was AO dash. This is O dash we have taken. This is AB divided by AO. AB divided by AO. This one, if you write properly, from division to multiplication, if you convert this line, it will become upside down. This AB you can cancel out. Then you will get AO by AO dash. Now let us see what is AO. AO is the focal length of the objective lens. It is towards your right from the objective lens. So we take positive FO. This is FO. Then AO dash. AO dash. It is the object distance for the eyepiece lens. It is towards your left from the eyepiece lens. So we take it as minus UE. This one can be written as M is equal to minus FO into 1 by UE. Then let us find out what is 1 by UE. For the eyepiece lens, if you use your lens formula, 1 by V minus 1 by U is equal to 1 by F. This is all for eyepiece lens, so FE, UE, VE I have written. Now let us see one by one. What is VE? VE is the image distance of the eyepiece lens. Image distance of the eyepiece lens, we are writing it as this distance of distinct division D. It is towards your left hand side, so you will take negative minus D minus 1 by UE. UE is towards your left, so if you use sign convention, it will be minus UE equal to 1 by FE will be positive, because for convex lens we take it as positive, it is on the right hand side, so it will be FE. So from here what you can get is minus into minus is plus, 1 by UE is equal to 1 by FE, minus becomes plus 1 by D. Then this term you can change it like this: 1 by UE is equal to 1 by FE. If you take common from the first term, everything taken out, so it will be 1 plus, there was no FE downside, so you multiply by FE plus 1 FE by D. Like this you can make it. And after that, this value of 1 by FE, you can put it here and then get the magnifying power of a telescope when the image is formed at a near point or the least distance of distinct division, that is under normal adjustment. Therefore, you can write M is equal to minus FO. This is minus FO, and this whole value is this term. Minus FO into 1 by FE will be minus FO by FE, 1 plus FE divided by D. This will give you the final magnification produced by a telescope under normal adjustment. Now let us see about reflecting telescopes. Reflecting telescopes. Nowadays, telescopes that we use are all reflecting telescope. Instead of using big lenses, we use concave mirrors, convex mirrors, and we make the telescope. There are two advantages. Later on we'll discuss about advantages and disadvantages in case of why reflecting telescopes are more advantageous than refracting telescopes. The first telescope that we are going to study, the refracting telescope, is Casa telescope. It's the name of the person who made a telescope. In Casa telescope, what he used was a tube type of structure like this, and this end he used a parabolic mirror. Parabolic mirror, if you say a concave mirror, this side it will be parabolic mirror. Then at this end he used a small lens, magnifying glass, convex lens, a very small one, and in the middle he used one convex lens. This is called your secondary mirror, this is your primary mirror, and this is your eyepiece. This is your eyepiece. This is second primary mirror. This is a concave mirror, and this is called your secondary mirror. Light rays that comes from infinity, that comes parallel like this, comes and strikes the parabolic mirror, that is a primary mirror which is concave in nature, and reflects here on this convex mirror, comes and strikes on the convex mirror. And once it comes and strikes in the convex mirror, the reflection, it goes straight to the eyepiece lens. So a person can view from here the image, a virtual image will be produced and will be produced behind this convex mirror. So this is how it works, the working principle. Now let us see the second type of refracting telescope, that is our Newtonian telescope. Newton made a telescope like this. The tube looks somewhat like this. Here you have the eyepiece. This is your eyepiece. He also used parabolic mirror, a concave mirror. This is the telescope tube. When light comes and in the middle there is a plane mirror, he used a plane mirror inclined at an angle of 45 degrees. When light rays comes and strikes those parabolic mirrors, as in case of Casa telescope, the same way it comes parallelly. After striking here, it comes this way and then gets reflected by the plane mirror, which is kept at an angle of 45 degrees. After reflection, the light rays, they go and enter the eyepiece lens, and then the image can be seen. Here also virtual image will be produced on the mirror, behind the mirror, that can be seen from the top. So these are the two Newtonian telescopes. One is Newtonian and one is Casa telescope, how it works. So you need to know the ray diagram, and you should be able to explain how the light ray comes, what happens. Is a converging mirror, concave mirror is a converging mirror, will converge and come and strike the plane mirror. This is your plane mirror. Inclined at an angle of 45 degrees. Light rays, after reflecting from the plane mirror, enters the eyepiece, and from here you can observe, from the eyepiece you can observe the image, virtual image, you will get it behind the plane mirror. Now let us see about the advantages of using reflecting telescope over refracting telescopes. Now let us see the advantages of using reflecting telescopes over refracting telescopes. And this is the most important part here. Several times in board exams it is asked. First advantage is that it is cheaper to make mirror than lenses. Large objective lenses to make it is very costly, but to make a mirror of larger diameter, that is larger aperture, it is much cheaper. That is the first advantage. The second advantage is that in lenses they produce spherical aberration as well as chromatic aberration, which in mirrors, parabolic mirrors, plane mirrors, you will not find such type of aberration. Now let me tell you about aberration. There are two types of aberration. One is called spherical aberration. Spherical aberration is defined like this: the inability of a lens to converge or diverge the rays at a single point. Like suppose if I take a convex lens, if I allow the light rays to pass parallel like this, then all of you know that it must come and converge at a single point. But if due to some manufacturing defect this curved nature is not okay, suppose bent or broken or something happens for manufacturing, or bubbling comes out in the glass, then the light ray, instead of coming here, it will go somewhere here. Like this it will pass. So it will not intersect at the same point, as a result of which the picture clarity will be distorted or will be disturbed. That defect of the lens, we call it as spherical aberration. The same way, the other aberration you have, that is chromatic aberration. In case of chromatic aberration, the quality of the color will not be good. Instead of red, it will appear faint red, that means it may become pink type of structure, pink image. So that disturbance also will be there when we use lenses instead of mirror. But in case of mirror, this type of aberrations are not present in mirrors. In lens only you can find this type of problem. That is the second reason why we prefer reflecting telescopes, not refracting telescopes. Thank you and have a nice day. Stay tuned with LFI Educate.